Welcome back to The Explainer. Today, we're diving straight into a monumental shift in artificial intelligence, how neural networks actually learned to process time, memory, and sequential data. You know, traditional neural networks, they're fantastic at analyzing static, frozen moments. But our world, well, it's entirely dynamic. So we're going to look at exactly how AI evolved to understand not just what's happening right this second, but how it connects to yesterday and what it means for tomorrow.
I love this thought. A picture captures a single moment, but a sequence tells a story. It hits the nail on the head regarding why traditional spatial AI, like convolutional neural networks or CNNs, completely fail at tracking data that unfolds over time. A CNN is absolutely incredible at spotting a cat in a photo because it processes spatial features like edges and textures all at once. But what about a speech recording, or a patient's heartbeat, or daily stock prices? CNNs process one single input and then immediately move on. They instantly forget. They have zero built-in memory to connect those dots into a cohesive story.
Just think about how unique sequential data actually is. The exact same words mean completely different things based purely on their order. If an AI is going to translate a language or predict the next word in a text message, it absolutely has to understand context, not just individual inputs. Like if I say, "the weather is very," and ask the AI to guess the next word, it needs to remember the start of that sentence to guess hot or cold, rather than just spitting out something totally random like car. So this brings us to a massive million-dollar challenge for AI. How on earth do you teach a neural network to retain memory from previous inputs instead of just instantly forgetting them? Think about your own brain for a second. You wake up, you remember what you had for breakfast, you remember where you parked your car. You're continuously connecting present information with past experiences. We needed a way to engineer that exact same continuous connection directly inside a machine. Enter the first major breakthrough, the Recurrent Neural Network, or RNN. And the big innovation here was the hidden state. You can kind of think of the hidden state as a mathematical notebook that updates with every new piece of information you hear in a conversation. Every single time new data arrives, the notebook gets updated. It squashes the current input together with the previous hidden state to create a brand new hidden state. Boom, you've got a chain of context.
If we unfold an RNN through time, you can really see how this builds. Notice how the exact same network cell is reused over and over again, passing its updated memory state forward step by step. I mean, the word recurrent literally means repeated again and again. We aren't building a brand new neural network for every single word in a sentence. Instead, the exact same network parameters are shared across time, which lets the model process sequences of any length, from a quick phrase to an entire paragraph.
But we run into a major roadblock, the fatal flaw, the vanishing gradient problem.
So basic RNNs are a great first attempt, but they suffer from a terminal issue when dealing with long-term dependencies. It's honestly like a giant children's game of telephone. When important information happens way back at the start of a sequence, the network just forgets it. Mathematically, this amnesia is called the vanishing gradient problem. See, during training, networks learn by sending their prediction errors backward. But in an RNN, that error signal has to literally travel backward through time. And as it multiplies through every single time step, the gradient shrinks exponentially. By the time it gets to the earliest inputs, the update signal is basically zero. The network completely forgets that those early inputs even mattered. Enter the heroic upgrade, long short-term memory, or LSTM. To fix this severe amnesia, researchers back in 1997 introduced a radically upgraded architecture. Instead of just a basic hidden state that blindly overwrites itself, the LSTM has a dedicated memory cell, a true long-term storage unit. It acts kind of like a student actively studying for a massive exam. It passes information through a series of really intelligent gates to actively decide what to keep, what to dump, and what to output. The forget gate looks at new input and decides what old info is useless now, like your GPS trashing an old turn instruction after you've already made the turn. The input gate decides what specific parts of the new data are worth writing down, and the output gate decides which piece of that retained memory should be actively used right this second. The secret sauce here is how it handles those new memories. Rather than brutally overriding old data, it takes the valuable, protected long-term memories and simply adds the most important new insights. This specific equation creates a mathematical shield against the vanishing gradient problem. It actually allows strong learning signals to flow all the way back to the very beginning of a long sequence.
Because LSTMs can actually remember those long-range dependencies, they unlocked some absolutely incredible real-world applications. We're talking forecasting hourly PM2.5 concentrations over several days to track wildfire smoke. The LSTM remembers a pollution spike from 72 hours ago and factors it into today's forecast. Or analyzing human gait and sports biomechanics, frame by frame. It can remember an athlete's initial heel strike and use that exact context to correctly classify the landing phase much later on. Plus, they became the backbone for language translation, machine health monitoring, and complex financial forecasting.
Next up, the streamlined successor, the Gated Recurrent Unit, or GRU.
Now, LSTMs are amazing, no doubt. But with 3 distinct gates in a separate memory cell, they are computationally heavy and pretty slow to train. So in 2014, we got a streamlined successor. By combining the forget and input gates into a single update gate and just completely ripping out the separate memory cell, the GRU gets you really similar performance to the LSTM, but with a much leaner design. It just uses an update gate to decide how much previous info to keep, and a reset gate to decide what past info to actively ignore, storing all that context directly inside the hidden state.
So how do you choose? Well, it's all about trade-offs. A basic RNN is fast, but the long-term memory is, frankly, poor. You're going to want an LSTM when absolute maximum long-term memory is absolutely crucial. But you switch to a GRU if you're constrained by compute power, because they require way less memory and train faster. GRUs are incredibly popular for things like wearable AI devices tracking human activity on the fly.
All right, let's look at sequence architectures and training.
Once you've actually picked your underlying model, you have to arrange it like a puzzle to fit your specific data problem. Not all sequence problems are the same. Image classification, that's a simple one-to-one setup. But what if you want the AI to write a caption for that image? Then you need a one-to-many setup. You could use a many-to-one setup to diagnose an abnormal gait from a whole sequence of joint angles, or to run sentiment analysis on a movie review. And for the heavy hitters, like translating an entire English paragraph into Korean or live speech recognition, you deploy a many-to-many setup.
Now, training these architectures takes some specialized wizardry. We use backpropagation through time, or BPTT, to calculate errors across the entire sequence. For super long documents, we use truncated BPTT to break it into manageable chunks. Then there's teacher forcing, which is a brilliant trick where we feed the AI the correct previous word during training rather than its own messy guess, which speeds things up big time. And if those gradients ever swing the other way and get massively large, we use gradient clipping to cap them off and prevent the whole thing from exploding.
But despite the massive revolutionary success of RNNs, LSTMs, and GRUs, they all share one terminal bottleneck. Because their core design relies on updating a hidden state step by step, they literally have to read data sequentially. Word 1, then word 2, then word 3, which means they cannot be trained efficiently in parallel on the massive modern datasets we use today. Processing 1 billion documents one word at a time, it just takes way too long.
Which leaves us with this profound question. What if an AI didn't need to remember everything sequentially, but could just pay attention to what matters most? What if we dropped the step-by-step entirely and just looked at the whole sequence at once? Well, that exact question sets the stage for the transformer architecture, the absolute game changer that powers all modern AI today. But we're going to have to save the dawn of the transformers for our next explainer.